Hello, I am going to make a presentation on SIS design, safety instrumented system design. Video is being taken on behalf of instrumentationtools.com and automationcommunity.com. Kindly watch and subscribe to the channel. What is safety instrumented system? Safety instrumented system, by the name, it refers to protecting personal, plant equipment and environment. In the process industry, handling various hydrocarbons, oil and gas, or nuclear and power plant installations, SIS layer acts as a protection layer above the process control layer, DCS, or alternately known as BPCS, Basic Process Control System. In the normal plant operation, controlling the plant for making changes to the various parameters in the process. The safety instrumented system layer is a protection layer which is just sitting above this layer. In the event of any hazardous events happen in the plant, SIS acts by using high performance fast acting emergency shutdown system to contain the hazard. So they have equipped with microprocessors to act quickly and then give the command to the valves to close or shut down the system, or to thereby protecting the equipment and personnel around. Various international standards such as IEC, ISA and ANSI governs the requirements of this design. We will look about it here. So these are the design standards what we talked earlier. IEC stands for International Electrotechnical Commission. There are two different standards which is applicable for the safety instrumented system. One is IEC 61508 and another one is IEC 61511. IEC 61511 is the one which governs many safety requirements standards. So this is the one for functional safety instrumented system for the process industry sector. This also describes in this standard about the SIS design, how the safety instrumented system has to be designed. And another different standards are ANSI, American National Standards Institution, Instrumentation Society of America, ISA. The ANSI and ISA have a common standard known as S84. So many countries have adopted this international standard, which is IEC standards, whereas ANSI ISA 84 is an alternate standard for IEC, being adapted in few countries like Western countries, US, Canada and all. This standard is being applied widely. Okay, safety instrumented system components. SIS is an instrumented protection layer which is designed to move the process to the safe state. SIS system comprises of sensor, logic solver and final control elements. This we have seen in earlier presentations also, and just we are refreshing to make it more clear and better understanding for the participants. Sensor, it's an instrument that measures the process conditions. Sensor devices that measure temperature, pressure, flow, liquid level, etc. Sensors can be for analytical instruments like gas chromatographs, oxygen, CO2 analysis, and electrical switchgear signals like power, current, etc. This is the one sensor what we are looking. Okay. And second one is logic solver. It is an intelligent device that performs logic functions to convert sensor input into an action command to be carried out by the final element. This is the one, the processor, the microprocessor, which is having a high performance and high speed capacity. This is the one from one vendor, one supplier known as Emerson. So this is a sensor and this is a logic solver. It will have different type of modules for taking the inputs from the sensors and giving the command to the final elements. That module is known as output module, and for the processing of signals it is having some centralized processors, microprocessor based devices. Final element, it is an equipment which performs the physical action commanded by the logic solver. Final element devices may be control valves, motor or switchgear, etc. Here we are seeing one butterfly type of valve. It could be a ball valve, or sometime it can be a switchgear equipment like some protection relays which is taking signal from the PLC, logic solver PLC, and making the pump or turbine or any equipment to stop. That is in the electrical switchgear panel. Okay, this is depicted in a different way. Process vessel, there are pressure measurement transmitter PT 1A, 1B. This is the tag numbers what we call it. So to identify the instrument. Here it is shown for the two different system. One is safety instrumented system with the one pressure transmitter sensor and one on-off valve actuator. And the same vessel is having a control element, control valve, wherein we have one pressure transmitter and a level control valve. So besides that, this system is having a one flow measurement also. A flow measurement sensor, pressure transmitter sensor, and is being connected to the basic process control system processor, and by internal logic the output is given to the level control valve to control the level inside this vessel. Whereas the safety instrumented system is taking a signal from this pressure transmitter PT1A, and if any hazard condition arises and this control valve is not able to control and the pressure inside the vessel getting high more than the designed limits, so this pressure transmitter 1A sends the signal and give it to the logic solver, and logic solver processes the logic internally and then gives the command to shut off this SDV, shutdown valve. So thereby the input to this vessel is getting contained and the pressure will get nullified. So it is similar one which is showing a different P&ID process and piping and instrumentation diagram. It's a part of a vessel. Again, this is a process you can consider like a chemical tank which is having a pressure measurement sensor, pressure transmitter, and here these signals are going to the safety sensors. This is having two sensors going to the safety instrumented system, and another one pressure transmitter, it is being used to do the measurement, and this signal is going to the basic process control system, and also it is having a flow measurement sensor. So based on the cell pressure, this is giving a command control output to the control valve and the pressure is being maintained. But in a similar case, the pressure cannot be controlled within the designed or allowed limits. So when the pressure inside the vessel keeps on increasing due to some reason, for example, this basic process control system is giving a command output and the valve is not able to close. For example, sensing the pressure getting high, there is a command going from the basic process control system processor to close the pressure control valve, but due to some internal faults or whatever reason, this valve is not closing and thereby the pressure inside this process getting high. So eventually and the pressure goes high. So these two pressure transmitter sensors senses this one and then gives to the safety instrumented system logic solver. Logic solver process the signal internally and then give a command to shut down these two valves. These two valves will get closed in this condition. So to ensure that the pressure is not getting further exceeded and protect the cell being exploded or further hazards happening. Here we are seeing the drawing about the safety instrumented system life cycle. This is a life cycle for the safety instrumented system, how it has been designed, everything. So it is having about 9 phases. In the phase 1 we are doing the conceptual design for the process, and phase 2 is having the analyze process hazards, determine the safety instrumented system need. That means how many transmitters, how many sensors and how many valves need to be installed, that is being designed. And next one is defining the target safety instrument integrity level. These are all coming in the part of LOPA, layer of protection analysis. We have seen briefly in earlier presentations. So these are all being in the part of the LOPA, layer of protection analysis study. And after this thing, it goes to the next phase, which is the design sys. So this is the topic which we are going to discuss in detail in this presentation and the forthcoming presentations. So this is the design phase of the safety instrumented system. Next one is based on the design. It goes for the installation phase, installation of safety instrumented system, and then commissioning of the safety instrumented system, and operate and maintain the safety instrumented system, and decommission in case of any need. One particular process unit is getting decommissioned due to the process change or any other reason, there may be a need to decommission the instruments which have been constructed in the earlier phases. So this is discussed in this phase. Actually, this is part of the IEC 61511 ISA standards. There could be some more phases which need to be studied and taken care, which we will discuss in further forthcoming presentations. Now we will go over the objectives of the safety instrumented system design. Safety instrumented system, different roles and responsibilities as per the company standard to be defined. For example, automation safety coach, design engineering lead, operation engineer or leader, technical center resource lead, etc. Each companies, according to the global location, geographical location, they have different standards based on the country, government requirement regulations, and the respective country's industrial board or whatever it is. So based on which the standards has to be developed for each company. Maybe it may be unique for some countries, it may be different for some countries based on the region, based on the safety requirements. Okay, so these are all the different roles who are participating in doing the design. And second one is develop conceptual design as per the safety instrumented system requirement. As we see, this is the first phase in the life cycle, the conceptual process design. What are the instruments has to be installed? What is the protection needed for the complete process? And based on which the layer of protection analysis will be discussed between with this team, and there could be some more members also as per the plant need, and it will be designed. So this is one of the objective. And review the SIS design like SIS sensor configuration, PLC or ESD system design, configuration, and final control element. Like what we saw in this one, here we have sensor, logic solver, which is a PLC, programmable logic controller, and this is a final control element. All this what is to be installed and what is the type of configuration, all these things has to be ensured. To ensure, reviews this design like this sensor, logic solver, and final element to ensure if the vendor's product meets the guidelines prescribed by the global agency such as ICSIDA or TUV. Actually, what we saw earlier is IEC, ANSI, ISA and all. These are the international standards. And ICSIDA or TUV, these are another companies who are doing the certification based on the standards, international standards. So all the vendors' products has to go through the certifying agencies to ensure that they get the relevant approval for as per the safety instrumented system design requirements. So this approval part should contain the instrument, whatever the instrument being produced, like pressure sensor, temperature sensor, flow sensor, etc. The instrument tag has to be implemented. The instrument range has to be marked in the instrument. Instrument response time has to be marked. Mean time to repair has to be defined. Mean time to fail has to be defined. And spurious strip rate has to be defined. There is one safety manual for each kind of instrument. So in this one, these parameters has to be defined for each type of instrument. Pressure sensors will have one set of values readings. Temperature sensor, flow sensor, everything will have different set of readings based on their internal calculations and the product type. Okay, ensure that SIS function, sensor final control element, shall work independently without affecting the controls. Earlier we saw there are two different layers. One is the control layer, which is having separate sensor, separate control valve, and safety instrumented system is having a different set of pressure transmitters and final elements. So here what is mentioned is each sensor and other thing need to work separately without affecting the control part. And there are some more objectives. Review the design specifications as per the safety instrumented system requirement. Develop conceptual design for safety instrumented system instruments such as proof testing, loop verification, and validation requirements. During the conceptual stage, design stage, proof testing, loop verification, and validation requirements has to be tabulated. Evaluate the design specification as per the safety instrumented system requirement with engineering, operation, and maintenance stream. There could be different requirement, different needs for the maintenance to do the routine maintenance activity, testing, calibration, etc. So this has to be analyzed during the design phase. Update sensor final control element configurations in the piping and instrumentation diagram. In the piping and instrumentation diagram, they have to be marked exactly identified as a safety instrumented system instrument, so that whenever the operation person or maintenance person who is going to attend will have extra care. Compare the conceptual design with the specification if it is meeting the SIS requirements. Here what happens, the design is being done by one set of people. They may be sitting either in the plant area who are directly involved with the regular operation team, or could be sitting in a different remote location and doing all the engineering activity and submitting the documents. So in this case, the design will be developed here by one company, like an engineering, procurement and construction contractor, whereas the installation and other part will be done by the different operating company. So there may be some gap. So whenever the design is developed, the instruments are going to be implemented and the instruments are bought, they have to be ensured that it is meeting the conceptual design requirements. This shall include proof testing requirements, whether the instrument valve can be tested online while running the process, or any alternate protection instruments in place to protect the people and environment. Process, there could be a possibility that only one instrument may be there, it is working and doing the isolation for a vessel. But for doing the proof testing, it is not possible to shut down those valves. Like in this case, see, in this case only one valve is there, so it is not possible to do the proof testing. Proof testing means we have to test the leak testing part, whether the valve is not doing any leakage or something. Passing, we call it as passing. The valve should not pass. And the operation, some cases depending on the process, it may require to close in 5 seconds, 10 seconds, like that. So these timings, those things need to be tested. So in this case, this particular example, it is not possible to isolate this valve. So there may be need of putting a bypass valve or any other isolation valve to ensure that the testing can be done. This is what mentioned in this point. Okay. Update the sensor final control configurations. This is what mentioned over here about the proof testing requirements, whether valve can be tested online or something, and alternate protection is in place. So complete hardware design, software program coding, etc. as per the design specifications. These are all the objectives has to be taken care during the conceptual engineering phase and as well as in the installation and commissioning phases. Thank you.